Hi, I'm Shashank Burigeli. I'm about to present a topic on a new fabrication approach of depositing different materials in a single IC. The outline of this presentation would be an introduction to the Moore's law and the nanoelectronics, and we will briefly discuss about semiconductor fabrication, and we discuss in detail about new single layer fabrication approach, and we'll conclude this discussion with what we have discussed. Moore's law, it's an observation that became a target. So Moore's law is an observation made by Gordon Moore in 1965, the co-founder of Intel, that the number of transistors per square inch on an integrated circuit has doubled every year. Since that observation, the companies have tried to double the transistors per chip, which rapid miniaturization and efficient high volume processing. The transistors were placed more than 10 power 19, 10 to the power 19 of transistors. This massive integration of transistor has made complex circuits in the form of the ICs inexpensive, and wide range application were practical and affordable. So the world went from microelectronics to nanoelectronics. So the graph here indicates the curve, how the Intel's 8008 chip had a 10 micrometer, and then now at present in 2016 what we have reached to 10 nanometers. The figure here shows us the stages of a graphical summary of the processing steps in the formation of a p-n junction diode, starting with a p-type silicon wafer until the chip is packaged. So it undergoes with all the masking, lithography, oxide, metal etching, and CVD deposition, chemical vapor deposition, and up to the metals deposition, and then packaging. So here in this you can see the different layers, and this pink layer shows the gate. Now in this new fabrication approach, the transistors are fabricated on the material in a single layer at a molecular level, which spans from 1 atom to 3 atoms width. And then they demonstrate an excellent characteristics such as excellent mobility for the chemical deposition of molybdenum sulfide, and ultra high on-off current ratio, excellent current density, and gigahertz RF performance. A single molecular layer of molybdenum sulfide consisting of a layer of molybdenum atoms sandwiched between two layers of sulfide atoms is shown here. As a 2D material, it shares many properties of the well-known graphene, such as excellent mechanical flexibility and high thermal stability up to 1090 degrees centigrade, while with a better band gap of 1.8 electron volts. It also overcomes the key shortcomings of the graphene for electronic applications, the lack of clear current saturation and pinch-off. The figure with the VI characteristics shows the output characteristics of the fabricated single layer molybdenum sulfide FET. With the device shows clear current saturation, which is due to the pinch up of the channel at the drain side of the gate at high VDS. Since the saturation voltage Vsat closely matches with the gate or drive VGS minus VD. This is the first demonstration of current saturation in top gated molybdenum sulfide FEDs, a crucial device characteristic that has been missing in previous reports. The maximum on-state current reaches 16 microamperes per micrometer at VDS is equals to 5 volts. The threshold voltage is at negative 2 volts, indicating that the material is unintentionally doped n-type during the growth and fabrication. The peak transconductance is around 3 microseconds per micrometer. The classical drift diffusion model accurately fits the device characteristics. Inverters designed based on this this fabrication approach can operate under a wide range of VDD from 0.5 volts to 5 volts with peak voltage gain close to 20 at VDD is equals to 5 volts. This breakthrough is this breakthrough is possible by the process of chemical vapor deposition process for growing single layer MOS. A ceramic board containing molybdenum oxide powder was placed in the center of the quartz tube, and a second ceramic board with sulfur powder was placed upstream. The substrate was pre-treated with a doublet of aqueous potassium salt solution and then mounted on top of the board containing the molybdenum oxide powder. During the growth, the furnace was heated to 650 degrees centigrade in argon environment. The sulfur vapor was carried by the argon gas and reduced the molybdenum oxide powder to form volatile suboxide, which diffused to substrate and was further reduced by sulfur vapor to form molybdenum sulfide films. The same approach can also be used to grow other semiconductors such as molybdenum selenide and etc. So I would like to conclude this discussion about the integrated circuits with a call for bidding farewell to Moore's law and adopting alternative approaches like using DNA in molecular electronics, DNA as a component, potential applications in nanotechnology and molecular electronics. In the field of molecular electronics, the connectivity of DNA is crucial, and DNA is a very promising molecule in the context of bottom-up based nano devices due to its superior self-assembly characteristics. A key tool in all the experiments that are presently undergoing is a dielectrophoretic trapping technique. In electronics, the new technology advancement or any new innovation is possible only when we think beyond Moore's law, as the doubling is already getting to falter because of the unavoidable power dissipation, and also due to quantum physics, limitations of quantum physics, we should just look for other technologies that can be promising. When we put power savings ahead of execution and get a lot more interesting.